T-distributed stochastic neighbor embedding, or t-SNE. t-SNE is a dimensionality reduction technique primarily used for visualizing high dimensional data in 2D or 3D space. Unlike PCA, t-SNE is nonlinear and focuses on preserving the local structure of data, making it highly effective for visualizing clusters. However, it is computationally intensive and best suited for small to medium sized datasets. Let's go ahead and implement this in Python. So I have a file already prepared. I'm going to go ahead and start. First, import necessary libraries. So from sklearn.manifold import t-SNE. This imports the t-SNE class from scikit-learn's manifold module. And as I mentioned, t-SNE is a non-linear dimensionality reduction technique particularly used for visualizing high-dimensional data in 2D or 3D by preserving the local structure of the data points. You need to remember that. Next, import numpy as np, which imports the numpy library, which provides support for numerical operations and array manipulations in Python. Next, let's get the sample data. These are points in high dimensional space. So I have x equal to np array, and I have the points here. Now this defines the feature data x as a numpy array where each sublist represents a data point in a 3D space with three values, x, y, and z coordinates. For example, 1, 2, 3, and 5, 6, 8, 5, 7, 8 are 2 points in 3D space. The shape of x is 7, 3, meaning there are 7 data points with 3 features each. Next, let's go ahead and initialize and fit the model. So I have t-SNE n components equal to 2, random state equal to 42. Here we initialize a t-SNE model with parameters n components equal to 2, which specifies the target number of dimensions for the reduced data. Setting any components equal to 2 reduces the data from its original 3D form to 2D, making it easier to visualize. Random state equal to 42 sets a random seed for reproducibility, ensuring that each time the code is run, the same t-SNE embedding is produced. Next, we'll do x reduced equal to t-SNE dot fit transform. This fits the t-SNE model to the data x and transforms it into a 2D space. Now, the fit transform both fits the model and applies the transformation, generating x underscore reduced, a new array containing the 2D coordinates for each data point. Unlike PCA, t-SNE does not capture variance but instead focuses on preserving local structure. So points that were close in high dimensional space will remain close in the reduced 2D space. Now finally, let's go ahead and print the reduced data in x underscore reduced, which prints the transformed data in the reduced 2D space. Now each row in x reduced represents a data point in the 2D space where the values correspond to the new coordinates derived through the t-SNE transformation. Let's go ahead and run this. Python t-SNE.py, run it, look at my points. Now when I run this particular code, I see a value error perplexity must be less than n samples, and I've not mentioned that. So I'm going to clear this out. I'm going to go here, and one of the things that I forgot was t-SNE n components 2. I have to give here perplexity equal to 5. That's another parameter that I missed. Now this one, perplexity, is a parameter in t-SNE that controls the balance between local and global aspects of the data in the embedding. It's usually recommended to set it between 5 and 50. Setting perplexity to 5 should work with 7 data points. However, if your data set grows, you may increase the perplexity to optimize the t-SNE output. So let's go ahead and run it again. And there you go. Let's compare. So if you see these points, this is kind of reduced to 2D, but making sure that they are in the same dimension. So now what we did here was this code kind of demonstrate how to use t-SNE to reduce a data set from 3D to 2D for visualization purposes. Now t-SNE is kind of particularly effective at creating visually interpretable representations of complex high dimensional data by clustering similar points close together, revealing patterns that may not be apparent in higher dimensions. So I hope this helps, and if you had any issues or have any more questions on this, let me know and I'll get back to you.